Kepler's laws 2. Kepler's first law says that planets travel around the sun in elliptical paths, with the sun at one focus. His second law says that a given planet will sweep out equal areas in equal times. His third law says that the ratio of a planet's orbital period squared versus the length of its semi-major axis cubed is a constant. This ratio has the same numerical value for all planets in the solar system. What this says is period squared, period is capital T typically, and the length of the semi-major axis cubed, there is a constant that holds such that this number cubed divided by that number, let's say squared, if you did that for every planet in the solar system, you'd get the same number. That's kind of cool. You might think, where did this come from? R cubed and T squared? How do you get that? Actually, it's not too difficult to derive that, and we're going to do that for you here in just a little bit. That third law is derived directly from two of Newton's laws, namely his second law, and then also from the force of gravity equation. Let's try deriving Kepler's third law. So here you can see on the right, we have a satellite of some kind, and it is going to be attracted to the planet with a force of Fg. The net force on this satellite is the force of gravity. Big G, mass of the planet, mass of the satellite, divided by the distance between them squared, which is given in our picture here as R. So there's the net force, and that should equal the mass times the acceleration of this satellite. Well, this is a centripetal acceleration, which we've said many times, centripetal acceleration is v squared over r. The m's cancel. One of those r's on the left gets canceled, and that means that the orbital speed that we have to have here is g big M divided by the orbital radius square rooted. We showed that just a little bit ago. But now, isn't the speed of this satellite, isn't it also equal to the distance around that it goes, which is 2 times pi times r, divided by how long it takes to do that, which we know is the period. V is equal to this, and V is equal to that. So if I equate these, then we should be able to find what we need. So let's try that. If we set that equal to the square root of gm over r, now let's do a little bit of work on here. Let's square both sides. If we square both sides, what happens here? This becomes 4 pi squared r squared over t squared, and then the square root sign here disappears. Gm over r. Now, what happens there? You can see that the r's are going to give you an r cubed factor, aren't they? See that? When you cross multiply, shall I do that for you? Let's cross multiply that. 4 pi squared r cubed is equal to gmt squared. That is the essence of Kepler's third law right there. R cubed is right there, t squared is right there, and all the rest of this stuff represents constants. Pi is a constant, g is a constant, m is the mass of the orbited thing, which for our solar system, that would be like the sun. It's the same for every planet, but r would be different for each planet, and t would be different for each planet. But if you take that ratio, that would hold for every single planet. So that, in essence, is Kepler's third law. And there are a couple of ways you could represent Kepler's third law. You could say, oh, t squared over r cubed is a constant. I'll just call it k. Or maybe r cubed over t squared, that's a constant. I'll give them names. I'll say constant 1, constant 2, because obviously they would be different. Or maybe you would see it as t squared is some constant times r cubed. Or maybe r cubed is some constant times t squared. It doesn't matter. The point is you have a t squared and an r cubed. Let's finish then by answering this pretty easy question. What condition exists for satellites for both elliptical and circular orbits, incidentally, that results in mechanical energy always being conserved? No friction in space. If there's no friction in space, mechanical energy is jolly well conserved.